Welcome. Today's lesson is on potential energy diagrams. We talked about these before in the last video on entropy, and here's a very simplistic potential energy diagram. Here we have potential energy on the y-axis and time on the x-axis, and we have a starting condition of high potential energy. This would be where the reactants start. And with time, the chemical reaction takes place and we get to the products, and it's at low potential energy. Anytime you go from high to low potential energy, we lost potential energy. How much? Well, the difference between these two numbers on the y-axis, that will tell you how much potential energy you lost. And if you lost potential energy, you had to gain some other type of energy, and that is heat energy. So we lost potential, we went down, so we gained heat, and so this is an exothermic reaction. And the delta H value is this amount right here is also equal to the delta H value. Right? And in this case, we lost potential energy. Our delta H value is negative, which is agreeing with the exothermic reaction. Now, it's a simplistic diagram because in chemical reactions, most of the time they need to be kick-started. So, for instance, if I have a Bunsen burner, before it will turn into a flame, I have to light it. So reactants, before they go from reactants to products, we have to kickstart them. And we don't call it kickstarting, although I kind of like to call it kickstarting. It's called activation energy. So we draw a bump because we have to actually add a little bit of energy to kickstart it, and then the process continues on. And so the amount of energy you need to add, which is from the start to the top of this hill, is called activation energy, and it's given a symbol EA. So we start with the reactants, which had high potential energy. We gave it a little kickstart to start breaking those bonds, and that's called the activation energy. And then it went to low potential energy of the products. So how do you get high and low potential energy in chemical materials? Well, products have low potential energy if they have very strong bonds. So if you produce something like nitrogen, which has a triple bond, that often has low potential energy. And high potential is often weak bonds. Those have a great deal of potential energy because they have the potential to react. So here we have a diagram of an exothermic reaction. Now, sometimes reactions, which we haven't talked about, but we will, especially in the next unit on acids and bases, actually can also go in reverse. So if this reaction went in reverse, we would change the products into reactants, and we would start down here. We would start here, and this would be the reactant side, and this would be the product side. And then we would go from low potential to high potential, and if we go in reverse, the reverse reaction is endothermic. And the reverse activation energy is from the start to the top of the hill, which is a lot of energy to go in reverse. So from here to here is the reverse activation energy, and we call that E for energy, A activation, and REV for reverse. So if this reaction did go in reverse, it would be an endothermic reaction, have a pretty large activation energy. So let's try another example. Here we're starting off with low potential, going to high potential energy. So hopefully you realize this is the reverse of the other one, and this is an endothermic process. And if there was nothing called entropy, these reactions would never exist. But because of entropy, some of these reactions actually do take place spontaneously. And here we have the reactants, just abbreviate that, and products up here. But once again, to get this reaction to go, you have to kickstart it or add some activation energy to break those chemical bonds. And so the hill actually goes higher than where we end up. And this is the activation energy here, the energy needed to start this reaction. So we call that EA. And then this is how much potential energy you gained from the start to the finish. That's my potential energy, which also equals my change in enthalpy, which is delta H. And this time it is positive. Okay, did we put that on the last time? That this then, the delta H is negative delta H. And this, we have a positive delta H. Now once again, if I did this in reverse, and some reactions can go both directions, I would start with the reactants now over here, and I would have a small activation energy for the reverse reaction, and it would go down to low potential energy, and that in reverse is an exothermic reaction, which I could write more like this first one. All right, so these are just ways that we can describe what's really going on in a chemical reaction. So what's happening to the energy involved in a chemical reaction? How much activation energy, how much potential energy, and then the potential energy change will be how much heat energy you gained or lost. So in your problem book, you're going to have to draw some of these potential energy diagrams, and it might be a problem just like I have here. So here we have a potential energy diagram. On the y-axis, I have potential energy and time on the x-axis. And it gives me some situation. And so now I'm going to see if I can draw this diagram. So I'm going to start, it says, at 30 kilojoules. All reactions don't start at 30, but we're going to start this at 30. So I start at 30 kilojoules. And it tells me that the delta H is negative. So hopefully you remember that is an exothermic reaction. And minus, so I lose potential energy. How much potential? 10. So if I start off 30 and I lose 10, I end up at the end at 20 kilojoules, right? But this is just a very simplistic way to write it. It doesn't include the bump yet. So we have to include that. That's EA, the activation energy, which is 5. And notice delta H can be positive or negative. You can lose potential or gain potential, but activation energy is always positive, right? You always have to add energy into the system to kick start it. So how much energy do I have to add before this reaction takes place? Only 5 kilojoules. So it goes up here to 35, and then it would come back down again. And as you can see, the shape here going from high to low is what we would expect from an exothermic reaction. So the problem after you draw it may ask you for some things. Here it asks you for the delta H of reverse and the activation energy of the reverse reaction. So how do I figure those out? Well, I look at my graph, and here is the change in potential. If I go forward this direction, oops, let me draw that a little bit better. If I go this direction, I go from high to low. But if I go reverse, I go from low to high. So I gain potential energy in the reverse. How much? I gain 10 from start to finish. And notice the delta H and the delta H of reverse will always be the same quantity, different signs. Activation energy, however, is not the same quantity and just different signs because they're going to have the same sign. So if I go in reverse, I start here and then go up to the top of the hill. So I go from 20 to here, which was 35. So the activation energy in reverse is from the bottom to the top of this hill, which is 35 minus 20. I have to add 15 kilojoules. And the reverse is an endothermic process. So let's try one more example, and then you can try some for yourself. So here I start with the potential energy of 30. It tells me I have an activation energy of 15, so I have to go up 15. 30 plus 15 is 45. And then it doesn't tell me the delta H. Okay, it doesn't tell me the delta H in reverse, but it does tell me the activation energy in reverse. So that tells me the distance from the very top to the end. So the top to the end is 10. Well, if I went up to 45, the end must be minus 10, must be down to 35. So I stop at 35, and here's my ending. So from the start, I started at 30. I ended up at 35. My delta H is here. And from the beginning to the end, I went up 5. So the delta H is 5 kilojoules. It's an endothermic reaction. What about if the reaction goes in reverse? Well, then I start here and go down here. So I go from 35 to 30. I lose 5 kilojoules. The reverse is exothermic. I lose potential and I gain heat. So there's a look at potential energy diagrams that explain how a chemical reaction takes place. So hope you enjoyed listening and try some for yourself. See you in class.